Professor Belfrost's computer science class is back!
Hi, welcome back to my class, and today I'll continue on explaining to you, yeah, number system. Okay, so this is the second part. Okay, I'm very sorry I didn't finish it the last lesson. Okay, very important things to do. I'm hurrying that time. Okay, so let's review a little. So in everyday life, we use mostly decimal system, but in computer system, we usually bring another more suitable system. Yeah, sometimes it's binary and sometimes hexadecimal, or yeah, sometimes we also use decimal number. Okay, so each numbering format or system has a base. Okay, what's a base? My base is the terminology used to explain how many symbols that you use to assign a single digit. How many we can use to assign a single digit. Okay, so binary numbers, the first system. It has base 2, okay, in which each binary digit called a bit. Okay, binary digit, this is shorthand bit, is either 0 1, and a bit on the leftmost position is called the MSB, and the bit on the rightmost position is called the LSB. And binary integers can be signed unsigned. Signed integer is positive or negative. Unsigned integer is always positive. Zero is considered positive in computer system, mostly. Okay, each digit in a hexadecimal integer represents four binary bits, and two hexadecimal digits together represent a byte. And a single hexadecimal digit represents decimal 0 to 15, and letter A to F represent decimal values in the range of 10 through 15. Signed binary integers are positive or negative. For x86 processors, then the MSB indicates the sign 0 for positive and 1 for negative. Okay, done. Let's continue on our left part. Okay, so negative integers. Okay, use 2's complement representation using the mathematical principle that the 2's complement of an integer is its additive inverse. Okay, it means that if you add a number to its additive inverse, then its time is 2. So how to express it? Okay, so actually it's very easy. Okay, we just need to infer a complement bits and try adding 1. And using the 8 bits binary value, for example 0000001, and we can complement it to be 11111110 and add 1, so it's the 2's complement here. Very easy, right? Okay, so it represents minus 1. Okay, very easy. So to create a 2's complement of an hexadecimal integer, actually also easy. Just reverse all the bits and add 1. So the easy way to do this without converting first to bit is that you just need to subtract the digit from 15. Here are the example. For example, you have 6A3D, then 15 subtracting with 6 is 9. Also, 15 minus A is 10, is 5. Okay, 15 minus 3 is what? C, right? Okay, 15 minus D, 2. Okay, plus 1. Then we have 95C3. Also, the second example shows you another good example. So use the following algorithm to calculate the decimal equivalent of a signed binary integer. If the highest bit is a 1, then the number is stored in 2's complement notation. Okay, it's negative. Okay, so create 2 complement a second time to get its positive equivalent. Then convert this new number to decimal as if it were an unsigned binary integer. But if the highest bit is 0, then you can convert it to decimal as if it were an unsigned binary integer, just as the first. For example, that you have a signed binary 111110000, and 1 is the highest bit. So it indicates this is a negative integer. So follow this rule. Then reverse the base all, okay? Then add 1 to the value from step 1. Also create the 2's complement. Done. Then convert to decimal. And it represents minus 16 because at the first time the sign digit, the highest digit of the sign binary is 1, so it's negative. I want you to learn this by yourself. Okay. So to create the binary representation of a signed decimal integer, then you need to do the following. First, convert the absolute value of the decimal integer to binary. Second step is that if the original decimal integer was negative, then create the 2's complement of the binary number from the previous step. So actually, the main thing that you need to focus on is how to use 2's complement. Because if you messing up with 2's complement, that it will mess up with your other calculations. Okay, for example, we want a minus 43 decimal, okay, to be translated to binary. Then first, the binary representation of unsigned 43 needed to be known first. Then, because the original value was negative, that we must create the 2's complement, okay, which is just reverse of the bit, inverse of the bit, add 1. So 110 10101 is the representation of minus 43 decimal in binary. To convert a signed decimal integer to hexadecimal, then first convert the absolute value of the decimal integer to hexadecimal. If the decimal integer was negative, then create the 2's complement of the hexadecimal number from the previous step. Convert a decimal, to convert a signed hexadecimal integer to decimal, then you need to do these two steps. First, if the hexadecimal integer is negative, you create its 2 complement, otherwise retain the integer as its. And the second step is that using the integer from the previous step, convert it to decimal. If the original value was negative, then attach a minus sign to the beginning of the decimal integer. Okay, so I want you to take a screenshot of this slide because maybe this is a very good notes. Okay, I have summarized in this slide. Okay, so you can tell whether a hexadecimal integer is positive or negative by inspecting its most significant or highest digit. Okay, so if the digit is greater than 8, okay, greater than or equal to 8, then the number is negative. If the digit is less than or equal to 7, then the number is positive. For example, you have 8A20. This is negative for sign, yeah, for sign 1. If unsigned, then you have no problem. If you have 7FD9, it indicates that this hexadecimal is positive. The signed integer of n bits uses only n minus 1 because 1 is reserved for, yeah, for the sign place, the leftmost one, right? Okay, so here's the table is showing you the minimum and maximum values for sign, bytes, words, double words, and quad words. Okay, so for these terms, okay, I want you to review back our last lesson. So subtracting a smaller unsigned binary number from a large one is easy if you go about it in the same way you handle decimal subtraction. So here's an example. For example, you are about to face subtraction of two binary digits. One is that the one equals to 13 decimal, and the second one is that the one that equals 7 in decimal. So how to do this? Yeah. First, subtract the bits in position the rightmost one. We have 0. Next position, move the next left. We have what? We need to borrow 1 from the next position to the left, right? And it will result in subtracting 1 from 2. Okay, so we have 1, but you need to uh, remember that you have borrowed a bit from the column, and now you also run out of a bit, so you need to uh, just borrow from the other column. So you subtract 1 from 2, then you have 1, and also finally the two higher bits are 0 minus 1. So you're done. We have 00110, which is equals decimal 6. A simple way to approach binary subtraction is to reverse the sign of the value being subtracted and then add the two values. This method requires you to have extra empty bit to hold the number sign. Okay, let's try. Okay, so first we negate the 00111, the second one, okay, by inverting its bits, then adding 1, producing 11001. Next, we add the binary values and ignore the carry out of the highest bit. So we do it like, yeah, simple, some summation, and it results in positive 6 plus 6. But because actually we have reverse it, then yeah, actually it's a reverse too. But this doesn't apply only for integers. Okay, we can also do for fractions. Okay, for conversion and also the operations. Okay, actually it applies for fractions. So for example, if we have the binary representation written with the integer and the fraction parts together, then the value of y for binary is actually two decimal. The equivalent decimal is the sigma I bi times 2 to the power of I. So for example, we have 1001 point or dot, okay, 101 base 2 equals to 2 to the 3 plus 2 to the 0 plus 2 to the minus 1 plus 2 to the minus 3, which is equals 9.625 base 10. I want you to check it again, okay? And to convert from decimal to binary from the fraction part, that we just repeatedly multiplying by 2. In first process to the 1 we do for the integer part, okay, and we take the fraction to be the next one to be multiplied by 2 again, as shown in this example. Okay, for example, we want to convert 0.81 to be the equivalent binary. Then we keep uh, multiplying by 2. Okay, first the first operation we get 1.62. Okay, so the 1 remains, the 0.62 get to be calculated the second time, times 2 1.24, and so on, so on, so on, until we find all, and that's that. This is actually not finished, but this only show you the 6 digit. Okay, but if in the B case we see that the fraction has been 0, then this is finished. That's why actually sometimes this fraction cause some problem in calculation, because the computer calculate in binary while we calculate in decimal, and sometimes because we cannot express the decimal to be the complete binary equivalent, we only take it to certain places and left other parts. Okay, that's why sometimes the computer and our hand calculations are a little different. For example, we are doing like subtraction or multiplication or exponent. Maybe it result the maybe you have tried before. For example, you are trying to calculate 2 times 2, it should be 4, but your calculator and computer results in 4.00000001 or 3.999999, because that it has some problem in binary representation. Okay, we need to take care of this. Okay, so done. Now let's move to the next topic of digital logic. So the digital circuit in digital computer and other digital systems is designed to be very analyzed by what we call Boolean algebra. This is very important. So Boolean algebra turns to be a convenient use in analysis and design of a function in digital circuitry, and we make use of variables and operations. So variable may take the value of 1 or 0, true or false, on or off. Okay, and yeah, the basic logical operation includes and or not. Later we'll know about NAND, which is not and, NOR, which is not R, and XOR, which is exclusive OR. It's just different operation with R. Okay, we'll see what's different between R and XOR later. Not are symbolically represented by dot, no, uh, and or not respectively are symbolically represented by dot, plus sign, and alpha bar. Though I prefer representing not with apostrophe if I type it, okay, because it's very not convenient for me to always switch to the equation bar and type the bar for you. So I always express it mostly in my last examples. You see later. Okay, for the first examples, maybe I still using bar, but later I use apostrophe. Okay. So the operation AND yields true even only if both of its operand are true. The operation OR yields true if either or both of its operand are true. and year operation not inverse the value of this number. Okay, so yeah, how about this one? Okay, consider the equation d equals a plus b uh, dot c. So if we expect d equals 1, then we need to have both or one of these term at least to be 1. So we maybe have a1 bc 0, a0 bc 1, or both a and bc 1. Okay, you have understood, right? Okay, good point. So several points concerning the notation. In the absence of parentheses, then the AND operation takes precedence over the OR operation. It is the same as mathematics, okay, as the general algebra. If we are doing multiplication, if you have multiplication and you have division, it will be run first, okay, before you're doing subtraction, addition, it will be run later. You have the rule PEMDAS, right? You have the law PEMDAS. Parentheses, exponent, multiplication, division, what again? Addition, subtraction, right? Also, actually, this apply here first. So actually, it's nothing difficult about digital circuitry. Okay. So here's the summary table. Maybe you need to take the screenshot first. Great to go. Okay, so for example, we have the expression a plus b but let's see. Oh, I'm sorry, b dot c. Okay, so a plus, it can be expressed through with a plus in parentheses b dot c or a plus bc. That's the same. So it means take the n of b and c first, then take the r, the ratio, and the a. Okay, so the table A above defines the basic logical operations and form known as the table truth. Okay, so this is all the table truth from six operations that are Boolean. Okay, not and, or, nan, nor, XOR. That's all. Okay, and I want you to not memorize this, but try to understand. Okay, what actually each operation wants you. That's represented in D actually. Okay. So, okay, here's the explanation of XOR. What is XOR? XOR is exclusive OR. So, exclusive OR only yields 1 if and only if exactly one of the operands has the value. So, you need to have 1 0 or 0 1 pair. Okay, no 2 0 or no 2 1. Okay, that's very important. Okay, so the logic operation, with the exception of not, can be reduced to more than two variables, as shown in the table B. And you need to also memorize some key identities of Boolean algebra, as some of them a little different from our basic algebra in mathematics course. Okay, I want you to take screenshot for the basic postulates and the other identities. Okay, so basic rules or basic postulates actually state without a proof, and our identities can be derived from the basic postulates. Okay, there are one of two this law is worth noting because it's different from what we would find in ordinary algebra or mathematical course, which is a plus in parentheses b dot c is not a plus bc. Yeah, it's a plus bc, I mean, but actually it can have another form, which is in parentheses, okay, or the sum of a plus a and b multiplied with the sum of a and c. Okay, so two most expression are referred to as the Morgan's theorem. Now we can restate them as follow: a or b equals to actually a naught and b naught, and a and b equals to a naught or b naught. Okay, actually there are bar and on the top of both, but I don't know why it's very small. Okay, there's an error on the machine. Okay, so you're invited to verify the expression that's shown in the previous table. There's your assignment. Okay, for today because there are no other assignment. Okay, so next we'll try to explain a little about logic gates. Okay, so the fundamental building blocks of all logic circuits. The gate. So logical functions are implemented by the interconnections of gates. Okay, so gates important. What is a gate? Gate is an electric circuit that produces an output signal. There's a simple Boolean operation on its input signal. Basic gates is the same as the logic and or not NAND nor XOR. Here's the figure that show the depiction of each gate. Okay, and note that not or inversion operation indicated by a circle. Okay, so we say that to assert a signal is to cause signal line to make a transition from its logical false state to logical true state. The true state is either high or low voltage state depending on the type of electrical circuit. Typically, not all gate types are used in implementation. Design fabrication are simple. Okay, so here's the complete set. And a not, or not, NAND, and NOR. So here's the figure showing you the use of NAND gates. Examples. Okay, but you need to understand this. And here's another for NOR gates. It needs to be clear that AND or NOT gates constitute a functional complete set. Okay, because they represent the three operations of Boolean algebra. Okay, actually we can synthesize the operation for AND and NOT operation. Also, the reverse is also true. Okay, it can be done as shown by the De Morgan theorem shown in this slide. Okay, so digital circuits can be frequently implemented solely with NAND gates or solely with NOR gates. Okay, and yeah, with this we have reached the most primitive circuit level of computer hardware. But we are mostly not only dealing with these things because we have what's called a combinatorial circuit. Also, we have a sequential circuit, and this is very important. Okay, so we have something that need to note. Okay, so a combinatorial circuit is an interconnected set of gates whose output at any time is functional only at the input of that time. Okay, this is very important. And in general, okay, a combinatorial circuit consists of n binary inputs and n binary outputs, and there are something that you need to note: truth table, okay, the graphical symbols, and Boolean equations. Okay, any Boolean function can be implemented in electrical form as a network of gates, and there are a number of alternative realizations. Okay, so here's the table show how to express um, f equals a naught b c naught plus a naught b c plus a b c naught. Okay, you see the one that results one is expressed in the equation. So this form of expression is called sum of product, SOP. And here's the implementation. I actually can create it as the second one. Okay, you see another expression. This is called POS, product of sum. Okay, and here's the implementation. I want you to learn it by yourself because it needs some time for you to try to draw it and understand it, not being explained actually. Thus, a Boolean function can be realized in either SOP or POS form. Okay, so yeah, the SOP has one term for each one, and the POS has one term for each zero. Okay, so there are other considerations. It is often possible to derive a simpler Boolean expression from truth table than either SOP or POS, and it may be preferable to implement the function with a single gate type NAND or NOR. And the significance of the first point is that with a simpler Boolean expression, the fewer gates will be needed to implement the function. There are actually three methods that can be used: algebraic simplification, count-on maps, and Quine-McCluskey tables. Okay. Today we will only discuss the first point, algebraic simplification. We will have two being discussed the next lesson. So algebraic simplification, very easy. It involves the application of the identities of previous tables that we have discussed in this lesson to reduce the Boolean expression to one with fewer elements. For example, we have this equation again. So actually, this can be shortened or simplified to be a naught b plus b c naught. How to be? Actually, to convert these two equations, you have any idea? Actually, you can return um, the second one to be duplicate. Okay, to be duplicate. Then you'll have the second after doing some manipulation. And also, this the second one can be written to be even simpler, which is b in bracket a naught plus c. Actually, you can factor out the b first, right? From the first equation, so b in parentheses a naught c naught plus a naught c plus a c naught. And also, you find out that this a naught c naught plus a naught c plus a c naught is actually XR, so it's a naught plus c naught, right? So this expression can be implemented as shown in the figure below. So the simplification of the first equation was done essentially by observation. For more complex expression, then there are some more systematic approaches needed. Includes two methods that we will discuss later. Okay, yeah. So here's inspiration for you today. Quote from you. So Leo Tolstoy once said, "Everyone thinks of changing the world, but no one thinks of changing himself. Start from yourself. Then, if you have made progress, then you may say you can change it." Thanks for watching. Here's your to-do list. Subscribe, give a like, comment, and share this video. I'll be back every Monday. Keep watching and be thoughtful. Oh yeah, one again is that we have run a website. Okay, so there will be maybe in future I will upload some materials there. It's called sciencewithexpressd.unaux.com. I want you to check it. So thank you again once again. Okay, see you again in the next lesson. Bye.